Hi. My name is Manuel Olbrich from Fraunhofer IGD and TU Darmstadt, and I'm talking about remote visual tracking for the mobile web. And by that we mean you just open a web page, use your webcam on your computer, and do augmented reality like we did years before in specialized applications which needed to be installed and all that. And the first thing to explain is why are we doing that. We all know web applications which are quite a nice thing to have because you don't need to install anything, you don't need to care for updates, in many cases you don't need to care about where your data is stored because everything is in the cloud, and it's pretty easy to have web applications where you can collaborate with others, share data, work together on the same data, and this simplifies many processes. And with X-Reading we have something similar. We have we don't have to install a player, we don't have to install any browser plugins, we don't need to care for updates, and as a developer I don't have to care for different versions on the player on different clients, because I know everyone has the same player because I'm delivering it with the web page. Also, the data is stored on the web. I don't need to care how the data gets to the user. As a web developer, I can easily implement applications where data between users is shared on the web, and I can easily create applications where users can collaborate simply with HTTP connections or websites. I also have the options to do server-side model optimization, which is usually a complicated process on my own machine. I need different tools to convert models to the right standard, and with web applications I can just upload my file to a specialized service which does the conversion for me. And when we look at augmented reality now, usually we have to install some kind of augmented reality application. So the user has to download the player and the content. We need to do some kind of camera calibration, and the client has to have enough power to do the rendering and to the vision-based tracking. And depending on the kind of tracking used, this can be quite power-consuming, and which is a problem on mobile devices, because we only have 2 gigabytes of RAM, which is I think the standard for current devices. You can do much less than a desktop PC with 16 gigabytes or more. So our idea is to have everything just in a web page. You don't need to install anything, and the tracking happens on a remote server, so you transmit your image to the remote server and just get the pose back, and you can use the camera pose to render your 3D model on top of the image. And how are we doing that? Different components, obviously the web browser, which we also use for image acquisition, since WebRTC was introduced into browsers. we have the option to get the camera image with get user media interface. We use Extrude for the 3D rendering. For computer vision, we use our computer vision framework called Instant Vision, which is a library we commonly used with the instant player for augmented reality applications, and the interface between the web browser and instant vision we use instant layout. I think most of you are familiar with Extrude. I know it's pretty easy to develop applications which are quite easy to use. It's always hard to set up a new application and think about the interface and design it. And with web applications, it's so much easier. You can just get any cheap web developer to do a good-looking functional interface for you. And another reason to choose Extrude was we already have very good experience with the 3D interaction model for augmented reality applications with Instant Player. So we already knew what we are getting into. And Extrude has really nice support for multi-punch interaction. So we don't have to care much about the interaction with the 3D model. The Instant Vision framework is developed in our department. We use it for all kinds of computer vision development and research. So years of research are basically combined in this framework. With different vision-based tracking algorithms and ranging from feature-based stuff to model-based algorithms. And like I said, we have a lot of experience with this combination with Instant Player. So basically every demonstration, augmented reality demonstration we showed during the last years was based on this. And it has a good scalability. So I can tune the parameters and get a low-powered version for mobile devices, or give it more power and run on the server. And that's especially interesting for our server-based approach, because we can basically scale it depending how much clients we need to provide service to. Instant.io is also part of our framework, which is made to use devices as nodes and Extrude applications. And the Vision Lab is one of such devices. And maybe has anybody here tried the Oculus Rift demonstration last year? Yeah, that was also made with Instant.io, where Tobias took the accelerometer data from the headset and used Instant.io to get the data to Extrude via WebSockets. And for our current paper, we extended that to not only rotations but matrices and images. So we can transfer images between the web browser and Instant.io, and we also added an back channel so we can send data to Instant.io, which is used by the vision. The image composition is quite easy, so we have just our camera image in the background, On top of that, we have our superimposed information, which can be 3D model or just some markers, depending on what we are trying to do. And again, on top of that, we have our user interface. So we can just use any HTML5 elements, since it's running in web browser, to design user interface, use any HTML libraries for that, and get pretty fast to a pretty nice and usable result. The basic data flow, we acquire an image with get user media, which we take in JavaScript and compress it into a JPEG image, and convert the JPEG image to base64 encoding, which is transferred in WebSocket to instant I/O. And this step is actually taking a lot of time, so that's currently our hardest problem to get this fast. Instant I/O takes the image, does the decompression, and pushes it into the vision, which computes the camera pose and returns the pose to instant I/O, which is then again transferred back via WebSocket to our client, and there we use it to render our 3D model. It's a short video which tries to show the process. So it's just Chrome and I'm loading a web page, and press a button, and the image is captured, sent to the server sends back the pose, and we are rendering the skyscraper model on top of the camera image. About performance, I already told you it's a problem with the image transport. It works pretty good in local networks, so using my laptop and have the service run on a Wi-Fi server, so it's pretty fast. It's not so good if I'm using a mobile device with a mobile connection. It gets the frame rate drops. Also, due to the JPEG compression, the frame size really depends on the camera. So if the camera image is pretty sharp with hard edges, the JPEG size goes up, and if the image is not so good, we have smaller image size, which is not so good, which is where we get higher frame rates due to the smaller image size, but for the tracking on the other hand, it's no problem when the image is not so clear. Possible solution to our problem is maybe WebRTC, which defines different video transfer technologies to send data to the web. And we are currently trying to set this up with WebRTC to get this a lot faster. Short table for performance again. There's a laptop and a local network, 30 FPS, no problem. But if you go to mobile devices, it goes pretty fast down, which isn't actually a problem really for mobile devices, because we can use inertial sensors in the mobile phone or tablet to do the tracking and use our vision-based tracking to get kind of keyframes to correct our tracking. and bridge the gap between the keyframes with emotion sensor. Like I said, this resolution WebRTC, because we can make better use of hardware acceleration. The whole implementation of the pipeline is native in the browser, and we just use JavaScript to set it up. While in our current implementation, everything is done in JavaScript. And we can use make optimized video codec instead of transferring single JPEG images like we are doing now. And we would also get rid of the base 64 encoding, which costs additional bandwidth. All of that what I just showed you, and the demonstration video I showed, you can try for yourself. We have a tutorial on the Instant Reality website. You just need to download the current version of the Instant Reality framework, start the server, get the website, which comes with the package, on the web server, and you can try it for yourself. We will also show the demonstration tomorrow in the showcase. So if anyone is interested to try it, just have a look, and thank you. And if anyone has any questions.
So very interesting presentation. You said that you use display the background image behind the combined videos, right?
Yeah.
Do you synchronize the update rate of the video and 3D content?
Currently not.
Okay. So you might basically just use the canvas element and render the video inside the canvas element whenever you get the response from the server to see the render. It's very easy to do that.
Also, a small problem is the delay between the pose from the server and the camera image. We can use the image we send to the server and send it back, so it comes in sync with the pose, which looks much nicer, but it uses additional bandwidth. So we try to avoid that. The demonstration, the table I showed you, on local devices, the delay is not much of a problem, but on mobile devices, you really see the delay.
So you don't have any markers that you put on there to see?
We can use a lot of different tracking algorithms. So we in my department and for the user of tracking, we do a lot of markerless tracking, which can be visualized in a lot of different ways. For example, we start to track the room or scenario like features and allow those features to the 3D model, which is used as feature list to check. Or we use a model-based approach where we take a 3D model, like a CAD model, and extract an edge image, which just shows the edges of the model, and compare that to the edges in our camera image, and use that for initialization. But yeah, we do a lot of markerless The demonstration I showed you was the image is also feature-based, so there's some setup step where the image is analyzed and features are collected, and the algorithm during runtime just tries to find those features again and knows where they are in space, so I can realign my 3D model to the image.
Other questions?
Seth, I have one. I'm curious about your ideas for some other kinds of trade-offs with different setups. So you're now sending a single camera image up for tracking. If all of the things went away, like that, the JPEG, the headers, the client's camera data going up, what about, could you use two cameras maybe better for tracking in terms of the stereo, or would that be a different kind of application?
There is research with stereo vision-based tracking in my department. I'm not really sure if we could do it with our browser-based approach. I think we can only get one camera through the interface, but we also tried this in a different setup where we have the server, the tracking server locally on our device, so it can access the camera by itself. And we just send the image and post to our web browser for viewing. And with this setup, we can use multiple cameras or even time-of-flight cameras or other devices for tracking.
Yeah, because I think there's a whole range of possible solutions, and I'm just curious as we think about the kinds of things that are next. So now you guys are sending a transform matrix of the object back to the user that's rendered.
Yeah.
There might also be the model where the server is doing the rendering and I just subscribe to a video stream, possibly.
Sure.
But both of those still have that issue of compositing. You know, if you don't have any depth information about other objects, maybe in between the marker and you, we're always going to have that 3D graphics just kind of pasted on top of the image, right? I mean, if we're in a collaborative environment and we maybe all have headsets on, as soon as somebody moves in front of a tracker, then obviously we're losing something. But I'm trying to think of recovering depth information from the scene. And that's why the stereo camera would be maybe useful.
Yes. We also did some research with depth cameras like Kinect or time-of-flight cameras. And with those you can pretty easily create a mesh from the depth data and use it for occlusion or even for lighting. So we had a demonstrator where you could point the camera at a table, for example, and you have your model rendered and it draws shadows on the table because we know the geometry.
And conceivably, if that uplink in WebRTC is, you could send a point cloud depth camera backup as well, possibly.
It would be a lot more complicated because we have our interface for web cameras with paid user media, but the Kinect interface is different.
Okay. Yeah, thank you.
One more question. I'd like it to see that you've not tested more and more people like the cloud, and you've not just tested the setup which works well, but also setups with less easy on the cloud with the Wi-Fi that can be set up. And I was wondering if you had any feedback about what does impact the performances of your system between uploading communication to the cloud, downloading, and for uploading and downloading the one-way and latency. I don't know if you have detailed feedback, for example, to be able to know if you had to improve performances, what should you do to want to be able to use the cloud with strange applications? What should we do in order to do this?
You mean what we need to do to improve the performance to a point where it can be used on a larger scale?
How can we define what the limits are? If we know that, for example, some bandwidth or some latency makes it impossible to process, to do your setup of the system, then we have a better idea of when to use or not to use the cloud. Because more and more people talk about the cloud, but it's not like there's one solution which will solve every problem, so we have to know when to use it or not.
Well, like I said, it works best in a local network environment, so if I have a good connection to a server, I can get a really high frame rate, and
you don't have more detailed, more specific about splitting these performances, measurements between uploading and downloading. You know, which is the part which is because if, for example, you don't have symmetric bandwidth, maybe uploading is part on which there is a loss.
yeah, the upload is really the bottleneck because we are pushing images up to the server, and for each image we just get a 4x4 matrix back. So download is really next to nothing, and the upload is a problem. But on mobile devices, like I said, you can use inertial sensor-based tracking to get over this by just using the vision-based tracking for correction. So you know when you took an image which you sent to the server, and you know where your device sensors, what device sensor data you had during that point in time. And when you get your metrics back, you can use the difference between that to correct your tracking. But this only works if you are tracking your camera. So if you are standing with your phone and tracking an object in front of your phone, you obviously can't use the inertial sensor data. And that's a scenario where it doesn't work really well. So you just get like 3 frames per second.
So, any more questions?
Yeah.
Just clarification, the latency that you report is the latency from you sending the image to the server and until you get back the matrix signal.
Yeah.
So in theory, to get the full latency for the R, you have to include the image acquisition and then the rendering. So we're talking more about the next 40-50 milliseconds. Is that correct? I mean, if you want to measure the full perceived latency for the user, you have to include the image acquisition as well as rendering and display latency. So we're probably, in the best case, talking more about 40 to 50 milliseconds. Is that like your estimate for the fastest case?
Yeah, I think so. The timing I presented was from after image acquisition to getting back the metrics. So for the pipeline.